Hello, everyone. I'm finally back after a few months, and I wanted to talk about linear transformations, but I thought I should probably talk about something a little easier first, because it's easier for me and for anyone who's seeing this for the first time. So let's look at the basics of linear algebra. Specifically, let's look at vectors and dot products. So let's look at just vectors first. I'll try to show you what a vector is, the same way that I was taught what a vector is, with a movie quote from Despicable Me. Honestly, I'm not sure if I can use a clip from the movie, but either way, this is actually a pretty good way to be introduced to vectors for conceptual and practical reasons. It's pretty accurate. Vectors are often represented as arrows pointing in a direction with a magnitude, just like Vector said in the movie. But what he doesn't mention is how we label a vector. We give them an xy coordinate, just like a point on a coordinate plane. The top number is the x coordinate, and the bottom number is the y coordinate. If we were in 3 dimensions, then we would have a third number for a z coordinate, but we're only looking at 2 dimensions. So here's a vector. Try to think of what the coordinates are, and don't overthink it. It's pretty straightforward. By the way, the tip of the arrow should be exactly in the middle of those 2 boxes, and the tick marks go by ones. So this is going to be negative 4.53, because we go back negative 4.5 boxes and up 3 boxes. So now that we know what a vector is, let's look at the dot product. So what actually is a dot product, and what does it do? So they are also called scalar products, which is a type of inner product, and it's a scalar valued binary operation on vectors. If you have no idea what that means, it's fine, because I'm about to tell you. So binary operation just means it's an operation that takes 2 inputs. So for example, addition is a binary operation. You take 2 numbers and you add them together for a resulting value, or in this case, a sum. Subtraction, multiplication, and division are all also binary operations, because you take 2 numbers and you perform some operation on it. Scalar valued means the output is a scalar. So a scalar value for computational purposes is practically just a normal number, like 1, 2, 3, or 15, or 25, or 3 halves, or 5.5, or whatever you can think of. Finally, it's an operation on vectors, which means instead of taking regular numbers, like scalars, as inputs, we take vectors as inputs. If you don't know what that last part means, it's fine, because I'm going to show you an example of a dot product later, and hopefully it'll make sense. So what does it actually do geometrically? So it takes 2 vectors and it multiplies their magnitudes, then projects one vector onto the other, then outputs the magnitude of that resulting vector. If we have 2 vectors, let's multiply their magnitudes so we have a longer vector in this case. Sometimes it's not as long if the magnitudes are less than 1. Then we project it onto the other vector. The dot product determines the magnitude of the length of that orange vector. If that's confusing, then here's another way to think of it. It's kind of like a measure of how much does each vector go in the same direction of each other. That might sound like a pretty vague explanation, so let's look at the computation as an example. Let's say that we have 2 arbitrary vectors, a blue one and an orange one. We can compute the dot product in 2 different ways. The product of the x coordinates plus the product of the y coordinates, or the product of the magnitudes times the cosine of the angle between them. These are 2 ways to compute the dot product, and as long as you're using the same 2 vectors in both of those definitions, they will always give you the same answer every single time. So let's look at the vectors 3, 4, and 4, 2. I didn't pick them for any particular reason. They're just easy to work with. So we can compute this as 3 times 4 plus 4 times 2, because it's the product of the x-coordinates plus the product of the y-coordinates. Or we could compute it as 5 times 2 root 2 cosine theta. Now, we don't know what theta is, so we can't do the second one, so let's just look at the first one for now. 3 times 4 plus 4 times 2 is equal to 12 plus 8, which is equal to 20. We just evaluated the dot product of these two vectors, but there's another really practical use for the dot product that I want to show you. We can use the dot product to find the angle in between those two vectors. Since we know that these two are equal, these two definitions, we can divide by the product of the magnitudes on both sides. Once we do that, we can also multiply by the inverse of cosine, or arccos, if you want to call it that. It's basically the same thing. Once we do that, we have now solved for the angle between these two vectors. I know its inverse sine is 2 root 2 over 5. I don't know what that is, but you can put that into a calculator and find out easily. If you ever get a question like that in school, like on a test, I'm sure they would give you easier numbers to work with. But that's all I wanted to show you in this video. I have a lot of ideas for the future, but it's really a matter of if I can do it efficiently, which, of course, hopefully I can. And off topic, but if you're like me, then you really don't like the shade of brown that I used in this video, because it's not the perfect combination of the blue and orange that I also used. In the future, I'm probably going to use hexadecimal, so I can do that. I can have the perfect combinations. So that's all for now. That's it for this video. I just wanted to have a relatively simple video. I'll talk about more interesting stuff in the future. Specifically, I want to talk about why a singular matrix never has a unique solution. But I thought I should talk about easier stuff first, which is why I made this video. Alright, thanks for watching.